So the plan today is to start at the top. So networks are designed to move data around. What I've tried to do to help, I'm going to send this out at the end as a PDF for anyone who wants it. I've tried to grade each page on sort of who it's more aimed for, but everyone's welcome to the information. If it gets a bit mathematical or technical, I've got a little red triangle. If it's things I think we should all know, I've got a little purple thing. And if it's just random info, a white square. So hopefully that will help people decode this. So start at the very beginning. What is data? Well, data can be anything we want on a computer or a device. A picture, some text, a number. What we have to remember is a computer thinks of everything as a number. So every letter, every character we see on our screens is translated into a number inside the computer. So this used to be done by ASCII. So on the left, you can see a large A is 65 and all of that. Nowadays, we need a lot more information. We had other characters. We defined this before for 26 letters in English. Now we have a lot more characters with accented letters from around the world. And with the advent of emojis, we need even more data to describe each letter, as every emoji is now described as a letter. Won't go through this page. Does everyone know what bits and bytes are? So a computer thinks in numbers. Actually, at the bottom, it thinks in things that are noughts or ones, either on or off. And we call 8 bits a byte, and that's a number. One of the more important numbers you probably all come across at points is the number 255, which appears quite regularly in network settings. That is the biggest number you can represent using 8 bits or 1 byte. So that would be all of those 8 numbers set to 1. Okay, so far? Basic stuff at the beginning. I won't go through these couple of pages. Gareth said they were pretty boring, but there's some information there for people to look at later. So what does a network need to do? Programs on a device or computer need to communicate with other programs or devices across a network or across a building. On a given device, say a computer, several programs can be running at once, all wanting to talk over the network. So on our radio computers, we have Radio World running, we have WSM running, we have WaveTool running. That's 3 different programs, all accessing the network. Every computer needs to be able to communicate over the same network. So every program has to communicate in the same way or same format. And the other part of what network needs to do is it has to send the data to the right device and to the right program. All seems fairly straightforward. So we all use networking called Ethernet. That's a protocol, it's a definition. We don't choose facts about that, but that's what everyone's been using really since the mid-80s. This is just some random facts. We can do Ethernet information over cable, over fiber, over wireless. And what Ethernet does, it defines how the data is moved between the devices. And the last fact for the more geeky is it sends 1 bit at a time. So if it's a whole big image, it will break that down into bytes, and then it will send each bit of the byte, 8 bits per byte, sequentially over the cable or the fiber. Everyone all right? Cool. So here's some bits and bobs about cabled connectors and different cable types. So you've probably, most of you heard of RJ45? That is those plastic connectors that you see down the bottom left. That's just a name. Unfortunately, as we've learned on lots of other courses recently, our industry and technical industries are full of acronyms and shortened names. So RJ45 is the name of the connector. And then you've probably all heard of Cat5 cable. Most people heard of Cat5 or Cat6 or Cat7 nowadays. This is just different standards for the highest amount of data you can put down a cable. So the chart on the left shows that category 5, we can put down 100 megabits per second. So that's 100 million bits per second. So how many bytes a second is that? Somebody. Or even to say how you'd work it out. No, you just divide by 8. Great. Thanks, Josh. Pay you later. And then we get to category 5E cable, which is what most of us use, which is 1,000 megabits per second. So a lot more data. and Cat 6, which some of us are now using, and then Cat 7 is 10 gigabits, 1,000. So what's actually in the cable? How many wires in a normal Cat cable? Who's terminated in RJ45?
8
wires.
8. So, and there are actually 4 twisted pairs of wires. So we actually think of everything as pairs. Why are you laughing, Dan? 4 twisted pairs of wires. So there's actually 4 circuits. For those of people that understand how audio works over balanced line, everything's done through twisted pairs of cable. It gives you noise immunity. It's one signal, but you need 2 wires, and it gives you noise immunity. So the twisted pair acts as one balanced circuit. For Ethernet signals, the type of protocol, we use different numbers of wires in this cable for different speeds. So a 10 megabit link, thank God we're not using that often now, only uses 2 pairs. And it's a transmit receive system. So one pair of wires is data going in one direction, and one pair of wires is data going in the other direction. On a 100 megabit link, we still only use 2 pairs, but we have to use a higher grade of cable, so category 5. On 1,000 megabits, you use all 4 wires, all 4 pairs, sorry. So one of the faults you can get with badly terminated network cableways is that if not all the wires are terminated correctly, a link will drop to 100 megabit, even though you're expecting it to be 1,000 megabits. That's just one of the things that can go wrong. Where to go? We also all know that there's a disparity of what people say is the maximum length for a network cable. Some people say 100 meters, 330 feet roughly, and some people say 90 meters. The reason why the 2 numbers exist is technically it is a maximum of 100 meters, but people say 90 meters because often when a cable hits a rack, we might go through a patch panel, then go through a patch cable before we get to the piece of equipment. So they shorten the length. I think that's about it for that page. Oh yeah, just bottom left, you'll sometimes see these other acronyms of UTP or STP. Sometimes there's an outer shield in the cable. This is something that is quite important over longer lengths because it gives us better noise immunity. And if you see on the pictures at the bottom there, the plastic one cannot be shielded. So being able to tell these cables apart is very important. If it's just a plastic shell, it cannot have a shield. You can sometimes get the plastic shells with a metal jacket, and then everyone hopefully should recognize bottom left is an Ethercon connector made by Neutrik that we should in theory see on all of our cables from good rental shops. And that will mostly be shielded. So people have probably seen these pictures before. So they make it in Cat 5 and Cat 6 mostly, they try to color code the cables. And you end up with a pair of wires that have some green, a pair of wires that have some orange, a pair of wires that have some blue, and a pair of wires that have some brown. We would say with the green, we'd have white, green, and green, white, orange, and orange. And those pairs should always be associated. Now, if you think about the cabling as a transmit and receive pair, what needs to happen is it comes out of the transmit of a device and needs to go to the receive of the next device. So in theory, we need to put a cross in the wiring, which is where the term crossover cable comes from. And you can see how you wire those. So at the top right, you can hopefully see that the TX wires on pins 1 and 2 and the receive wires on 3 and 6. Long legacy to why they're not adjacent. And then to make a crossover cable, you can see how the wires cross between the transmit pairs 1 to 3, 2 to 6, 3 to 1, 6 to 2. On the left is the color codes for the 2 different ends of cable. Now, fortunately, we don't have to worry about crossover cables much nowadays because most equipment auto switches. So it detects whether it wants to be a transmit or receive. So we don't have to worry about it. But people will often argue about the wiring standards, the color codes you're meant to use for each end of the cable. The standard that most people tend to stick to is this one called 568B, and that's the order that makes sense for most people. But it's good to be able to know that the 2 different standards exist, and you can just simply compare either end of a cable to know what's happening. Everyone okay to there?
I assume that those 2 different types of cable are not cross-compatible.
What do you mean?
Well, if you end up with a mixture of 2 different
As long as both ends of the cable are wired the same, it's absolutely fine, as long as you keep the pairs of wires doing the right job.
Okay.
So one of the things that has happened in Cat7 cable, seems to be with the Tor grade Cat7 and others, they now just use 8 different colors. So you have to actually really be careful about keeping pairs of wires associated together. So when you cut the jacket off and look inside, you have to look for the 4 different pairs being wrapped around each other and use them as a pair. But it's vitally important that both ends of the cable are wired the same, but you keep a pair doing the same job. So you must always have a twisted set of wires on pins 1 and 2, pins 3 and 6, pins 4 and 5, and pins 7 and 8. If you don't, you end up with some very strange faults, as a few of us have been through. Does that all make sense to everyone? Dan's smiling because he remembers.
Russ, why doesn't it run straight with 3 and 4, 5, 6, 7, 8?
It's an old legacy thing down to old phone cables. So the older plugs are, some of us may remember on phone handsets or UK phone sockets, only had 4 pins. And they designed to use the 4 center pins of the bigger connector. They used to make a receptacle they could all fit in.
Ross, is there any easy way of knowing what you said, but possibly if you lose a pair when you're running at on a gigabit network, your speed would reduce. Is there any easy way of identifying that fault?
Yeah, mostly by looking at the speed indicator on network switches.
Yeah, absolutely. Okay.
But it is something, if you have a cable that pins 1, 2, 3, and 6 are good, but any of 4, 5, 7, and 8 are broken, the link will drop from gigabit to 100 megabit. But seemingly you wouldn't know.
Okay, thanks.
All right. Everybody else all right? Somebody else was talking. I don't know who it was. Okay, cool. So that's network over copper, or cable as we call it. So quite often we want to run things a greater distance. Not in our industry so much, 100 meters tends to be good, but in broadcast and arenas, they quite often need to run further than 100 meters. So the only real way to do that is to use fiber and light down the fiber to transmit the network signals. Now, in the same way that category cable, we've all probably, can anyone think of a use that we use for category cable and RJ45 connectors that's not for Ethernet network? Most of us who've done GOS shows will have used category cable for linking a device that we use all the time, but not for network.
CCTV?
CCTV is an example where we use the same cable. Another one?
CAN bus.
CAN bus, thank you, Mike. So, and the same applies to fiber. Just because it's a fiber doesn't mean it's got network on it, but we can make Ethernet network signals go down a fiber. Fiber's becoming more common, and especially fiber multi-cores. I think Andy and Matt and a few others have done several shows now in the UK using fiber runs. And it's something we're going to start doing. They're more reliable, and the multi-core fibers are now really small and easy to use. So we all now need to know a little bit about fibers. Fundamentally, there's 2 completely, almost different types, and that's single mode and multi-mode. They have very physical different things. So in a single mode fiber, the internal glass wire, or not wire, but glass strand, is only 9 micrometers. I couldn't be bothered to find micros. 9 micrometers in diameter. That's pretty damn small. Maximum length for single mode is around 40 kilometers. And there tends to be 2 standards of wavelengths. So 1310 and 1550. To give an idea of where that sits compared to light, it's not actually visible light. It's below the infrared. Multi-mode fibers tend to have a strand either of 62.5 micrometers in the older standards, or 50 micrometers is more common. Maximum length about 1 kilometer. And they tend to use 850 or 1300. The reason why wavelengths are very important is the way a fiber works is it bounces light through the fiber, keeping it within the walls using refraction. We won't get into that, but if you put the wrong wavelength for light down the wrong fiber, it won't come out the other end. It's the simple thing. So you have to treat it as a fact you have to know. In the same way, a radio receiver, we set a frequency of 450 megahertz. Pack and transmitter have to be the same. A wavelength is just expressing the frequency in a different form. So we have to make sure that both ends are the same frequency, otherwise something won't talk. In the same way that category cable has different standards, there's different standards of fiber. These are multi-mode standards I've listed at the bottom, and it shows for different data rates the maximum length you can achieve with that type of fiber. From my basic research, it seems most rental shops are going with OM3, which at 1 gigabit links gives us a 550 meter range, and at 10 gigabit, which is something we're going to start getting into soon once the video departments make it cheaper, is going to be about 300 meters. Just to put this in perspective of another signal we can put down fiber, I think a few of us have ended up having to do some MADI links over fiber. So instead of BNC, we use MADI. And the data rate of a MADI signal is 125 megabits. Just to put it in perspective.
CCTV out in New York is becoming a thing on fiber as well.
Absolutely. Just because you can get more bandwidth down the cable. Everyone okay with those bits? Any questions there? Great. So this is probably slightly unfamiliar ground for some people. So most people know what a network connector looks like, an RJ45. These are different connectors that we use inside racks as patch cables for fibers. The two on the left are the ones that are more common. So you get LC, which literally stands for little connector, and they are about 5 mil square, and they are not square. I couldn't find a good enough picture, but the bottom edge is slightly rounded, so one edge is slightly rounded. And in that picture, you're actually seeing two fibers there. In the same way a network link has a send and receive, fiber at our level only can send light in one direction. So you need a send fiber and a receive fiber so data can travel in each direction. At the bottom is another connector that certainly people that have seen RME products will know, which is called SC, which stands for square connector. Those are the two that are most common in our side of the industry. But on the right, people can have a look later. There's bayonet connectors, screw connectors, and various others. Okay. So, principle of fiber and crossovers. So, as I said, in copper, in cable network, we used to have to make crossover cables between every device, but now it auto switches. With fiber, we have to cross over between devices because the input part of a device is a light receiver and the transmit part is a light transmitter. So we have to make crossovers. As I understand it, the standard is actually to make every single link a crossover. So if you look at the picture in the middle of the two LC patch cable with handy color code, if you orientate those connectors to be the same way, you'll notice at one end of the cable, one fiber is on the left, and at the other end, the fiber is on the right. So it would cross. On a multi-core, so on the right, I've drawn one of the standard connectors that's used for two pair fibers, so two fibers, which is from Nitric. You'll see that I've shown diagrammatically that in the cable, in the multi-core, it crosses end to end the same way. So that's the standard. Now, if you go back, if you look in the middle on our patch cable again, if we were linking these two RME devices together, you can now see how the output would go to the input and the input to the output. Now, because we can't see the light, we can't really tell which way is transmit and which way is receive. So we have to be very thorough on this stuff. And quite often, if a fiber link isn't working, it's where a cross hasn't been made somewhere in the line. So that concept okay with everyone? So in the same way that we have multi-core connectors in audio, same happens with fiber, and especially because we need two fibers to be able to do a data link, one traveling in each direction. Top left is probably familiar to some people. Anyone remember what or SUL is used for in some places.
Digico.
Digico HMA, or more accurately, Opticore, which Digico used. HMA was just two fibers in a connector designed to be incredibly rugged and tour-proof. That made a connector. You look at the size of the connector and you think that the piece of actual transmitting glass is 9 millionths of a meter, and that's the size of connector we need. And the reason you need such a large connector is two reasons. One is so you don't snap the glass, you give it complete protection. Secondly, when you make a fiber connection, it's imperative that the two fibers point very accurately at each other, straight on, not at an angle. Otherwise, they don't pass the light between them. The other pictures on this page are nitric connectors, which again seem to be becoming very standard in the entertainment industry. They've come up with very catchy names like Optical Con Duo, which is two fibers in a connector. So that's good for one link, transmit, receive. Then you have Optical Con Quad, which is quite popular in video because that gives you two links. So you would use a link for transmitting your video and a link for data. And then the bigger multi-cores nowadays are 12 fibers or 6 pairs, which is called MTP12. And then they also now make MTP24, which is 24 fibers or 12 pairs. When you're using those, what tends to happen is the multi-pin plug goes into a box at each end of the rack at front of house, the rack in your substage. And then on the back of that box is 6 or 12 dual LC connectors that you can then patch to different pieces of equipment. So how do we get Ethernet down these things? Well, another acronym coming along here, which is SFP. And these are little modules that are standard that convert electronic signals into light, send and receive. And a lot of network devices have slots for these modules. So top right is a Cisco switch, and on the right-hand end, there's 2 slots for SFPs. Each SFP is a send and receive in one box, so it's a complete link. And if you look at an SFP on the left, you'll see it's got 2 holes, and LC connectors fit in those holes. So a dual LC will fit in that SFP. Bottom center, for those who may play with Avid a lot, on every Avid AVB card, they also has SFP slots. So you can either use the copper connector, the RJ45, or you put an SFP module in and convert it into 2 fibers, send and receive. Now, in saying earlier that we have to be careful with fiber and frequencies, if you linking 2 network switches via fiber, you need to put the same speed and the same wavelength of SFP at either end of the link. So both switches would need the same. I think unless there's an exceptionally good reason on our shows, we should always use the same speed and frequency for every link within the network we're building. This keeps it simpler for fault finding and looking. So remembering back to the page earlier, we can put an SFP module in that's Ethernet at 1 gigahertz, 1 gigabit per second, sorry, 1310 nanometer, etc., etc. And we would tend to use, and most rental shops in theatre and rock and roll are using multi-mode because it's an awful lot cheaper and we don't need to go much further than 500 meters. How's that for everybody? Great. Here's where we have to be slightly careful. I sort of mentioned it earlier, I jumped ahead. Just because something has SC connector for fiber or an RJ45 doesn't mean that it is for Ethernet. These devices on this page, we've already talked about DMV amplifiers in the top. That's an old D6. It has RJ45 connectors, but if you plug that CAN into a network switch, it won't work. An R70 is a particularly dangerous device as it has network and CAN. And then bottom right is an RME, which is MADI, and it's nothing to do with network over the fiber. So they're just other uses you can have. Cool. That's sort of that area. Is everyone sort of okay with the physical side? Any questions or things you've seen that...
Russ, can I bring up one point about the LC connectors in the fact that they can easily be, the ends can easily be taken apart and put together the other way?
Absolutely.
People
So
know.
Yeah, that's very true. So you can buy these dual
They also
patches.
break, really.
They do. So one of the things, when you buy these, you can buy them in these pairs, but the plastic clip that holds them together as a pair, you could easily pull out the fibre from and swap them. So you could make it straight again or not cross. So you actually need to be quite careful with fibre patch cables to check it before you build your rack. I think that was your point, Andy?
Yeah, exactly. Yeah.
It's a very good point. And yes, you have to treat them with respect and care. And to be honest with you, if you're building a show and they haven't come out of a sealed bag, it's worth making sure we buy fresh ones in general for a show. Thanks, Andy and Dom. Anything else? Cool. Okay. So the simplest network you can come up with. 2 computers and a piece of cable. At that point, any data that leaves the left-hand computer is going to arrive at the right-hand computer, and the same going the other way. So that doesn't need half the other settings that we come on to. This is a bit more like what we do. So we might have multiple computers, and we put something in the middle of them that joins them all together and makes sure the data gets around. And there's 3 main devices for that. There's a hub, a switch, and a router. They are all different terms and do different things. So we need to understand, by the end of this, hopefully we'll understand some of those terms. Now, in our own homes, we're probably actually a bit more familiar with networks than we think. So we might have our computer, our mobile phone, our TV, PlayStations, all connected via Wi-Fi to our home hub or broadband box, or whatever you might call it. It's slightly different in America. And then that, using the telephone wires in the UK, will go to the exchange, where it will go onto this mythical thing called the internet, and then we can get to different servers around the world, e.g. Netflix. Now, this magical box that sits in our house is actually 2, 3, 4, 5 different devices in one box. And that's sort of where we need to get to understand some of these different terms. So a switch is a device that can link lots of computers together. So this magical box contains a switch. It contains a Wi-Fi access point, which is how you can convert cabled Ethernet to Wi-Fi. Has a DHCP server, and a NAT router or network address translator, and an ADSL modem. Let's not worry about the last 2 in there, but an ADSL modem is how it converts Ethernet signals to travel over phone line. So we've probably mostly all got one of these in our house, I would think. You're all using it right now to talk to me here. So diving back into this hub switch router. At the moment, a lot of the words on this page won't mean too much to some people. So what's important in this second is that hub we should never be using anymore. And it works with a layer 2 MAC address. I'll worry about that in a second. We have an unmanaged switch, which is we'll often call a dumb switch. We have a managed switch, which can work at layer 2 or layer 3, and the router layer 3. So we need to start understanding what some of these things are. So what a hub does is it was a very dumb device. Data arriving on any port, any socket, is sent out of every other socket, regardless of whether the right device is on the end or not. So that uses up bandwidth. So for every message any computer sends, it will send it out to every single other computer, whether it wants it or not. The difference between a hub and a switch is a switch learns which socket to send data to. So data arriving on a particular socket only leaves on the socket that it knows the destination device is on. This means we're not sending data inefficiently to every computer, meaning we have much more bandwidth available because each link is only used for what it's needed to do. So that's why we should never ever use hubs anymore, and I don't think they're even sold anymore. But somewhere at Orbital there is a box of them, so have to not use those. Hubs and switches, to work efficiently, they need small chunks of data to deal with. Ethernet, this magical network standard, decides to send messages in what are called packets, up to 1,522 bytes at a time. This sounds a big number, but actually is very little data. If more data is needed by the application, so we're sending a picture between two computers, then it splits it into smaller chunks, smaller packets, and sends each of those one after each other. Okay for there? So, unmanaged switches. Unmanaged switches, they don't have IP addresses themselves, so you can't configure them. You should only have one network on it. So in our world, we often have show network, and radio network, Dante. And you should, if you're working with unmanaged switches, each unmanaged switch should really only have one network on it. Hopefully you'll understand why by the end of this. And it doesn't matter which port you plug any of your devices into, as they'll all be joined together. Pretty simple. When it comes to managed switches, we have to be a lot more careful. And a lot of our shows are starting to use them. So managed switches have to be configured. They don't just route signals between each port. And they will have an IP address, and then we'll log in either using a web browser or a serial link if you're clever, and we'll configure them. A managed switch actually enables us to split it into many parts in one switch. So on an unmanaged switch, we said you should only really have one network connected to a unmanaged switch. We have a show network with the amplifiers, radio network with the receivers. With a managed switch, with configuring them correctly using VLANs, which we'll do another time, you can actually make a managed switch inside split itself into many different switches. So it is possible to plug amplifiers and radio devices all into one switch. Now, because of that, we have to plug devices into particular ports. And that is done in the setup in the warehouse. But if you ever have to swap one of these out, it's really important to remember that everything must go back into the same place. Hopefully, if we've been good production, we will have left a picture on them saying what each device is connected in. The other thing to remember about a managed switch is they actually take a little while to boot up. Most of them take about 3.5 minutes to start. As Nate kept saying to me on Diana, the network's broken every day, and then 3 minutes later he was happy again. You have to allow these switches after power up to boot before they'll start transmitting data. If you manage to turn everything on very quickly and try and use programs, so R1 to talk to the amplifiers, it can take up to 3-4 minutes before you'll be able to see or connect the amplifiers. So something to remember.
Is it worth then having these switches put onto hot power instead of UPS power? This is sort of a conversation that's going on quite a bit. What do you think the rule is on that?
It's tricky. The whole, my personal view on UPSs and things like that is a UPS can fail at any, as well as a hot power. I think in general, if the rack has got UPS power, I tend to be inclined to put network switches on UPS. If I'm doing Dante, I try to put a network switch, one on hot, one on cold. But I think, to be honest with you, now with the point you've raised, I think putting on UPS is probably a good idea.
I mean, I think the point that's worth remembering about UPS is that somebody said to me the other day, oh yeah, but you know, if we go onto UPS, it's so that, you know, we can stop the show gracefully. If you go onto UPS power, you aren't stopping anything gracefully. The only purpose of UPS is to be able to save and shut down without losing your data.
Which therefore, absolutely, and therefore the logic probably should be put all your switches on that, because you can be able to access more of your devices if they still have power.
I mean, we also quite often see setups where, like, the monitors aren't on UPS.
Yeah.
And of course, it's a fundamental problem. The idea is to shut down gracefully, but if your monitors and Add-a-Link switches and things like that aren't on UPS, then you can't do that. I think it's really worth thinking of UPSs as the ability to shut down gracefully, and also potentially that they have quite sophisticated surge protection stuff in them. So it's worth putting delicate equipment on the other side of a UPS. But the idea that you might somehow be able to, like, stop the show gracefully under UPS power is flawed, I think.
To be honest with you, I think front of house UPSs should be on, and other places it's not so important to worry.
Yeah, we're also more and more running network-based comm systems, and at that point, 100% they should be on UPS.
Yes, and consideration given to where racks, remote racks are sitting with COM network on. Absolutely.
Comms, of course, is the alternative to that, in that the whole purpose of the UPS on the comms is to allow stage management to gracefully stop the show without killing anybody. So everything involved in comms and radio comms should be on UPS if possible.
Yeah, I think it's something we definitely should consider. Cool. Which way is down? That way. So here's an example of labels I've been doing for managed switches, which shows for which connector. So if you look at the switch, you see the layout of the connectors. For which connector goes to which device. So QLab 1 machine, QLab 2 machine, system 1, system 2. And then below is a load of information that we'll come on to next week. That's just an example I'm doing. I think everyone now shows doing managed networks leaves a similar picture. But it's important if you're there as the person with the show every day to vaguely understand why we leave these pictures, and you must plug the same devices back in the same place if you have to reload them. So this thing called bandwidth. So why do we care so much about how our networks are built? And it's to do with bandwidth. More and more nowadays, we're using more and more data-centered devices that all need networks to communicate. Our networks, from when I first started touring on shows, we used a network to connect an access point to a system computer so we could tune the system. That was the extent of the network. Nowadays, we're connecting comm systems, we're connecting program page mixers, all kinds of things, all onto a network for ease of access. So we need to manage our data better. And in fairness, something on Diana, we actually found a bottleneck in one or two of our links, which we'll come on to next week. So just going back to Ethernet, on cable or fiber, the standard links at the moment are 10 megabit, 100 megabit, or 1 gigabit. We're starting to see 10 gigabit be available on the very expensive switches nowadays. This is maximum data rate down an individual link. So what's important is we only send data from a switch to a device that that device requires, so that more communication can be had. If a link runs out of bandwidth, too many things want to try and communicate, there's two things that can happen. The worst one, and is actually what happens quite often, is the data is lost. So either has to be resent or is lost altogether. And that means devices, that's where you get the R1 timeout errors and various things like that. I think that's about the whole point there. So how would a network work? If you want to send things specifically between devices, what do we need to know? Well, we need some kind of address, like postal mail, or we say, this is this computer, and I want to send a message to this computer. We need a way of addressing. Secondly, we need to send a reply to address, so that the receiver can know who to reply back to. We also, because we can have multiple programs running on a computer, all using the same network, we have to send some kind of information to say which program each message is for. That's the basics at the beginning. So this is a scary sort of picture that some people at university might have seen, or real network nerds have to look into. And it's trying to show how messages and the build-up from an application at the top down through various things in the computer get out onto the cables or fiber. We're not going to worry about too much. We're going to break this down. So the very bottom of this is this thing called MAC address. So between the physical wires, once we get back to data, the first thing that we deal with is MAC address. So this, some of you might be thinking, well, hold on, we've heard of IP address, but what's MAC address? Why do we need another address? And actually, Ethernet standard only actually talks about MAC address. So what is a MAC address? It's nothing to do with a Mac computer, which is the first thing to say. Windows computers all have MAC addresses too. Every network interface, so some computers have cable, they have a wireless, in theory has a unique MAC address, unique to the world, in theory. This address we can't set. Well, you can if you're bad pirate people, but you're not meant to be able to set. And every device you buy will come with a MAC address hard programmed into it. It's 48 bits long, which is 6 bytes, or some very big number of addresses that's possible. Now, quite often you'll see it written in hexadecimal. Each of those pairs of characters represents a byte. I'm not going to go into hexadecimal today, but it's another way of writing a byte out, which a byte can be a number between 0 and 255. So, for example, in decimal, GOS tablet's Wi-Fi MAC address is 240.213.191.65.218.
No, don't tell. No, what?
We all have to know that to set routers up, Gav. It's important. That's the unique address of that device. So if we want to send a network packet to GOS computer, that's the address we can send to.
You don't. No, you definitely don't. No.
So now we have an addressing scheme. So every single network packet on an Ethernet network has a sender and destination MAC address added into that packet of data. So a packet, just reminding you, a packet, if a program wants to send a big, large image, it will get split into very small packets. Every single one of those packets needs to have a sender and destination MAC address added to that packet. So we're moving the amount of data we can send at a time, but we need this information. Every switch in the world will deliver network packets using MAC addresses. So earlier on, we said that a switch learns which device is on which port. It learns which MAC address is on which port. Just a reminder that an Ethernet maximum packet size is actually quite a small few number of bytes. Out of that 1522, which seems like an odd number, 22 of those bytes are used for MAC address, send and receive, and other synchronizing information, leaving 1500 bytes for the actual data itself to send. Just a random bit of information. So here we go now with a real world drawing. Now this is getting into the world of understanding how the network works. So on a day-to-day basis, this is not information you need, but when you start configuring managed switches and for high level of fault finding, this is useful information. So two computers connected to a switch, and computer A wants to talk to the server. So I've written on the screen what the MAC addresses are of these different devices. Remember again, MAC addresses we cannot set. When you buy the hardware, it's hard programmed into it. So just reading the slide, computer A is connected to port 1, computer B connected to port 2, servers on port 5. So computer A wants to send a message to server. It transmits a packet which has a destination address matching the server's MAC address, and it also puts its own MAC address in as the reply address. So the switch knows that the destination MAC address is on port 5, so only sends that data back out of port 5. So we haven't wasted bandwidth on the port 2 cable to computer B. Yeah, everyone okay with that principle? Cool. Now, if we have two switches involved between, then switch 1 will still learn that that MAC address is on port 5, and it doesn't really care that it has another switch in between. So it will still forward the data through that path, and only out of the particular ports it needs to get there. Make sense? So the way I've sort of been talking is actually a type of messaging called unicast, which is one device wants to send a message to just one other device. So very specific. There are some reasons on a network why one device might want to talk to many devices. We'll come on to some of those a little bit later. Now, there is a special MAC address defined that tells a switch to actually send that packet to every single device connected, so it will come out every single port. And that's with all bits set, or all FFS, or all 255, depending on how you want to think about it. And it's known as the broadcast address. So when a switch sees a destination MAC address of that, it will actually send the packet out every single socket on the device, regardless of IP address, for those that are maybe 10 steps ahead in this conversation. That concept between unicast and multicast makes sense to people? Yeah? So in our world, we all have examples of broadcast messages, which we'll come on to in a bit, but one that you'll hear quite a lot of us talk about is radio receivers. Radio receivers broadcast out their data, saying receiver A is 10% RF and the person's screaming. is actually broadcast out to the receivers. The destination MAC address is set to this. So it means every single switch that is connected to those receivers will forward those messages out every socket. And the effect of this is we waste bandwidth on things that don't need them. So only our radio computer or front of house computer needs those. Nothing else needs this information, but that's how network routing works. So, okay, we've talked about MAC address, but most of us will have heard of IP addresses. So trying to embrace the Windows and Mac family at the same time as I do some of these. So on the left, this is a window I hope most of you have seen on your Mac at some point. Yeah, looking at people that I don't see very often. And on the right is the same Windows version. And the Mac actually is a bit clearer for what we're trying to talk about. Surprise, surprise. There's three numbers on that screen, or three sets of numbers. There's the IP address, subnet mask, and router address. And I'm hoping we can explain the first two of those today. So why do we need MAC address, IP addresses as well? Well, MAC addresses, this is actually to do with the internet more than anything else. MAC addresses are randomly distributed across the world. So in our building, every single computer, amplifier will have very random MAC addresses. And we can't predict them. And they're hard numbers to know. And they're not very user-friendly to remember because there's no logic to them. So for the internet, you would need to be able to send a packet specifically to anywhere in the world. You would have to learn where every single MAC address of every device was in the world, which is a ridiculous amount of data for every computer to have to learn and remember. It would be much more efficient to have an addressing system that we specify, and then we can say, this range of addresses are all in the UK, this range of addresses are all in the US, so that the routers around the world know where to send the packets so they can reach their destination. So IP, and quite often you see V4, version 4 is what it stands for. There are many versions of IP, but IP version 4 is currently the most common. So the smart people will tell us that version 6 is coming soon, but not seeing it that readily in the domestic market. So actually on every device to communicate on a TCP/IP network, which is what we call networking over Ethernet nowadays, has to have an IP address. On the internet, every IP address is allocated by an independent body. And they make sure that they are a subset in each country, so we know where to send the message. I've got a picture like this, which helps explain that. So my home to the internet might be 83.45. Gareth's home, these aren't real numbers, so you can't do any nasty things to it. Gareth's home, Netflix, BBC. And the way the internet actually works is any address with 80 to 85 as the first number is in the UK. Any address 1 to 21 is in America. And there's various other ranges. So an IP address, what's it made up of? Well, it's made up of 4 numbers. Each number is 1 byte. So that means it can be 0 to 255. That gives us 4,228,250,625 unique addresses in the world possible. Now, when they came up with IP version, this whole IP address system, they actually thought that would be enough addresses for every single device in the world. That is now incredibly wrong, now that all of us in our house probably have at least 15 devices, at least. Every device needs a unique IP address. Otherwise, you don't know where to send the data. And an IP address is sometimes known as a layer 3 address. And I didn't put the picture back in. And the reason for that is in this model, we start at the wires at the bottom. Then we convert it back to data. And then the first thing we look at is the MAC address. And then the next thing we look at is this IP address. It's called layer 3, just randomly. One way. Boom. So we don't have enough addresses to give every device in the world its own IP address as well. So they came up with a solution that makes a lot more sense. Instead of one giant network for worldwide, we actually make lots of small networks, or LANs, which stands for local area networks. That, if we want to, we can connect these smaller networks to the internet, which is what we do in our homes. In our home, every single network in our house is a LAN. It's an isolated network that your home hub or the broadband device will connect onto the internet. Now, for LANs to work, we need to still use IP addresses, and we need some addresses available out of the possible addresses of IP. So special addresses have been set aside to only be used on LANs, so they cannot be used on the internet. Every single LAN in the world can reuse these same addresses. What's important is that the address has to be unique within the network, each individual network. And at the bottom, there's touching on the subject for next week, which is that the way we connect LANs to the internet, because it is through a translator, because we're all using the same addresses again and again. So to try and explain what I mean, here's two different homes. Inside our house, we might have 3 devices. A computer with an IP address of 1.100, TV 1.101, my phone 102, and equally in somebody else's house, the same addresses are used if they are the allowed addresses. And our home hubs or routers to the internet will have an IP address as well, but similar form to what we use for devices. And then it has a public address, which is a completely different number. And that public address is unique across the whole internet. Yeah.
So where does NAT come into this?
That's exactly what NAT is. It translates all the addresses inside the house into one public address. So any device in the house that wants to talk to the internet will communicate to the hub at the router address, and the router will translate the sender IP address to its public IP address. That's how the message goes across the internet. Then when a reply comes back, it comes back from the internet to your public address, and your router remembers who asked for the data and changes the destination of the sender, their destination address, to be the internal address again. That's what NAT
does. That mean that when you're communicating across the internet and people say, oh, we can look up your IP address and see who you are, what they actually mean is they can see what router you came through. They can't tell who you are. With
your router address, your public router address.
So if there's 10 of you living in a house and
I don't know which one of you, it's not quite true. There is some metadata somewhere you can read, but it's not. It doesn't give you the whole picture.
Surely they'd be getting the MAC address of the computer.
Correct.
Okay.
Yes.
So if you manage to hack into the router...
Well, actually, they don't get the MAC address. I apologise, Mike, I'm wrong. The MAC address gets translated.
You only get the MAC address of the router and the IP of the router.
Correct. The public IP.
So the guy hacking the CIA from the Starbucks coffee shop could be any of the people in the Starbucks.
Yeah, there are other bits and bobs that you can pick up on, but yeah, fundamentally, yeah, your hacking career can move on a step.
Thanks.
Unless they use that information to get into the router and look up the logs of the individual addresses inside it.
Yes.
So that data is stored inside the router.
For a time, yes. So that's just to try and explain a bit about the internet, but we don't really connect the internet. So if our little local area network is not connected to any other network, including the internet, then it doesn't matter at all what IP addresses we use. We literally could use any number for those 4 parts of the IP address, as long as every device on our network has a unique IP address. However, if at any time our internal network needed to connect to the internet, so maybe we want to put a computer using its Wi-Fi to upgrade software or something else, then we have to have used these special addresses that are reserved just for local area networks. Otherwise, problems occur. I'm broad stroking this here for those that understand this in a bit more detail. Now, bringing it back towards what our shows do, most of you will have heard of us say 192.168 about 1,000 times during every prep. And that's because we have chosen a particular range of addresses out of this private addresses that you can use, that we use on every show. In actual fact, the audio industry as a whole seems to have chosen these addresses. And they range from 192.168 with 0 and 0, all the way up to 192.168.255.255. And that gives us a possible of 65,536 devices on our networks, which Gareth has not broken yet. Yeah, that's just a choice we made. This very boring sheet shows us why we made this choice. And this is an internationally agreed set of numbers. This is not really for anyone to remember, but it gives you the different ranges of IP addresses that are reserved that cannot be used on the internet, apart from Class E. That's apart from the multicast. Don't worry about the claims, but often you'll see on lighting, a lot of you will have seen on lighting networks that they tend to use 10 dot as their addresses, and they have 10 dot in 3 different numbers for their devices. That's just a choice they made to use that range. We've used Class C, which is the numbers we already said. There's a few other sets on here that I'll just point out for the moment. There's this thing called zero config. Anyone who's done Dante work will have seen 169.254. We'll come on to that when we look at Dante network. That's another private range of IP addresses. So that's how we've chosen our numbers. We didn't pull them out the air. There's this international set of agreed numbers. So why would we want to separate our networks? And it's all to do with bandwidth. More importantly, broadcast messages and bandwidth. But we'll explain hopefully in a second. At the time, where are we? Oh, we're okay. So within a building, we make more than one isolated LAN. So thinking about from a technical point of view, on a show, there'll be a lighting network, there'll be a sound network, video network, the ticket system network, bar sales network, and a backstage office network. These are mostly always separate within a building. But in reality, we might want to divide these networks further. 2 sort of reasons for that. One is like a logical human brain. So we know this range of addresses is the comm system. This range of addresses is our amplifiers. This range of addresses is our radio receivers. It makes it easier to understand. The second reason is to deal with broadcast messages. Remember that a switch will forward the broadcast message to every single device connected to it, regardless if that device wants it or not. So examples of on our shows of different networks and the names that we sort of use. So we'll call a show network. And on that particular network, we will have our amplifiers, console, show control computers, system computers, and the wireless access point for system tablet. On our radio network, we will have all the radio receivers, the main radio computer with WaveTool, and all other computers using WaveTool and WSM. On some of our shows with digital comms, we'll make a network for that. So it'll have all the Helix net on it, or Readall, or whatever we're doing. And then on some shows, we'll also have a Dante primary network, which is audio. And Dante has needs two networks, primary and secondary. So this is the number of networks we have just on our most shows nowadays. So looking a bit further into the segmenting of networks, I think I've actually said everything on this page. Yes. So going back a few years, this is what we used to build. So at front of house, we'll connect all our show computers together to one switch, and we'll call that our shows control switch, show network switch. Then at the radio rack, we'll have a switch that's dealing with show network as well. And we'll connect another switch with all the radio receivers together. And that will also connect to the radio computer and to the system computer front of house so we can see the things. And in our amp room, all our amplifiers get together and then connect back to the show network. Most people, that makes sense, that drawing? That's how we used to do it before VLANing and managed switches. So we're going to try and stick to this concept. And the reason we did that, hopefully will explain here, is to do with the radio receivers are broadcasting messages all the time, and they will flood the network with this packet by separating them physically on different switches. Not every device is having to receive those messages. That's the whole point that we did that, to increase bandwidth. So we can look at that picture and go, there are two networks. But how does a computer know that we have two networks? Well, every device on those two networks needs to have unique IPs, so they have to be unique across both networks, not a single common number. That we did. But computers and network devices cannot tell that the networks are separated. They will treat them as one network unless we tell them some other information. So what we actually want to try and do is give each network a network ID and then a device ID within that network. And this is where subnet masks come in. So a subnet mask tells the computer how to split an IP address into two parts. First part tells us which network it is, so we give each network an ID number. And the second part is which computer or device on that network. And it's a way of telling it how we're splitting it. Now, can people from this set of IP addresses here, which is common to us, see how we've split our network? If we were having to describe to somebody, how would you identify which address is on which network? What would you say?
Last two sets of digits.
Two sets?
So you've got the 1.10 range and the 3.40 for the radio range.
Almost. You have to treat the first three numbers as one item because they're the same for each individual network. So actually we're saying 192.168.1 is our network identifier. And then the last number is the device identifier.
I think what Mike's saying is that the first two sets of numbers, in theory, are pretty much constant across.
I am being pedantic as I'm known to being.
No.
Everyone goes to the spacebar. So we can see how we've split the numbers, but what a subnet mask does is tells the computer that was our logic. So I've said half of this. Said all of that. So as you can see, you've worked it out. 192.168.1 we use on our show networks. 192.168.3 we use on our radio networks. On the show network, every device has a different last number, but all have the first bit. Now we describe this way of splitting the number using a subnet mask of 255.255.255.0. Now for those of you that don't want to know much more, that's all you need to know. That you have to set the subnet mask correctly as the network was designed to be. And on our shows in general, other than Dante, that is the number we use. Delving in a little bit deeper, what it's actually doing is it's telling, by saying 255 is a whole byte, and it's actually saying each one of those numbers in the subnet mask represents a number in the IP address, and it's actually saying if the number is an on, a 1, 255, then that number is to be treated as a network address. The way we've chosen, I've just jumped slides. The way we've chosen to split our networks up is we have network 1 has addresses of 0.0 to 0.255. That's 256 addresses in each of our networks. That's not quite true because in reality we can only use 254 of those. The very first address, i.e. 0, is reserved by switches. And the very last address, 255, is how to do a local IP broadcast message. Don't worry about that for a minute, but actually we can only use 192.168.0.1 all the way up to 254. You'll never see 255 or 0. I'll leave this page for some people another day. There's a bit more information there of how it works for those that want to look into the maths and the bits. So now we've sort of looked at IP address, and hopefully most of you understand a bit more on that. Why do we still need a MAC address? And the important thing to remember is a network switch only worries, an unmanaged network switch only worries about the MAC address. It doesn't care about any other information. Yet in all of our programs and software that we use, you won't ever type in a MAC address. You'll only ever use IP addresses. So how does this work underneath? If we look at R1 wanting to talk to two amplifiers. So R1 wants to send some data to an amplifier. It knows the IP address of that amplifier is 192.168.1.101, a number we chose, but we've set that up. That happens in this model, if the program's at the very top, so inside the computer, it works down this model. So we're on the right-hand drawing, we're at the very top, we've got R1, and then we know its IP address. Now we need to work out what Ethernet needs to know. Ethernet needs to know the MAC address. So when a computer first runs, it has no idea of anybody else's IP address or what their MAC address is. So how do we get this message across? For Ethernet to work, we have to know the MAC address of the computer. So what Ethernet came up with, and IP, is a system where a computer can ask the network, hey, you with this IP address, what's your MAC address? Now, most of us don't need to worry about this, but again, when you're setting up managed switches, this is something that's important to make sure we don't block how this method works. This all happens under the hood. We don't have to worry about it. But when we set networks up or are fault finding, a Mac computer caches this information for a very long time. Windows doesn't. What that means is if we change the IP address of the device when we're configuring it, our computer will no longer re-interrogate. It knows what the MAC address is for that device, except it isn't anymore. So quite often when we're in stores, that's when we get these problems where a device seemingly disappears if we've changed its IP address without rebooting a computer. Through this mechanism of where the computer says, hey, who has this IP address? What's your MAC address? This all happens under the hood. So now what goes on? Now we know the MAC address. So inside our computer, R1 says, I want some data from an amplifier. It sets the destination IP address. Then at the bottom part of our computer, it will ask who has that the MAC address. It comes back. And now we can send the data to the switch and it gets to the amplifier. So that's actually how a message gets across the network. So just pushing even further this point of why radio receivers and we split them off onto different networks. The way a radio receiver broadcasts this message is it sends to the IP broadcast address for that network. Now, in theory, that should only go to, we would think that that should only go to computers with a 192.168.3 prefix. But the thing that's actually forwarding the messages around the network is the switch. And the switch only cares about the MAC address. So in order for a message to be sent everywhere, we have to set the destination MAC address of all ones. Again, this is all done by software. So the effect is the switch will still send that packet to every device on the network, including a computer that's got a different IP range. In theory, we've told it is in a different network because the switch doesn't care about these different networks. So we've wasted bandwidth. What actually happens in the computer is these messages arrive because the switch sent it to them. We checks the MAC address while it's set to the broadcast address, so we say yes. But then the next part of the network layer says, oh no, this isn't meant for me on the QLab machine because it's in a different IP range. But it's still wasted bandwidth on the cable. I'm not sure I've explained that particularly clearly, but does that make sense to people? Anyone can help me with specific questions? What it's trying to do is explain why a broadcast message wastes bandwidth. I don't know if I've done that well. What did you say, Gary?
Makes sense to me.
Yeah. So that's why we care. So that's why we did this. That's why we do split out networks. So there's one last piece of the puzzle that's missing for sending a message. Right back in the beginning, we said that a network needs to know destination address, receiver address, but we said that on a computer, many programs can be running. So how does the network part of the computer know which program a message is for? And this is where, unhelpfully, we've reused the same name. So a network switch will refer to each socket as a port. In the network message, there's a piece of data added called a port number, which are not the same thing. And a port number tells inside a computer, like a mailbox, which program the message is sent for. So let me explain. So we've probably heard of port 80. Port number 80 on a computer is for HTTP, which is otherwise known as web browsing. DS100 OSC messages get sent to port 50,010. These are just numbers that you find for each device. And we don't have to know that. The software uses these numbers. So the way it works is a program will take its data, say, I want to send that to this IP address, which assigns the device, and I want to send it to this port number on that device, which then tells it which mailbox to send it to. And then on the receiving computer, every program registers to read a particular mailbox and only gets the data intended for it. But what is confusing is a switch will refer to its sockets as a port, and computers and devices refer to a port, meaning which mailbox on each computer to send the data. That difference makes sense to people? It's an annoying thing they use the same name. Yeah, cool. So the final part of the puzzle. So if we want to send an OSC message from QLab to a DS100, the QLab program will know that the DS100 IP is in this case 192.168.1.19, and it knows that a DS100 likes to receive OSC data using mailbox port number 50,010. It works down inside the computer, and the IP layer checks the destination and says, yes, I know how to do this, and decides which network interface is appropriate based on the network address. So that's the first part of the IP address. Then it passes to that device, that network interface, where it will find out the MAC address of the DS100 if it doesn't know it. And then it will send it out the computer with this MAC address. The switch goes, this MAC address, I know where that is. That's on port 1. That gets to the DS100. Then inside the DS100, we'll check the MAC address to check it has received a message valid for it. And it goes, yes, that's my MAC address. Then it passes it up inside itself, and it goes, yep, that IP address this message is for me. And then finally, it puts it in a mailbox 50,010, and the DS100 software goes, yes, here's a message from R1, from QLab. So that's the structure of how a message gets across the network. And given just how much data we send, this happens for every single message. Yeah? Sort of going to change topic if people are okay. Any questions on that? I've laboured a lot of that, but a lot of those principles become really, really important when we get into managed switches.
Is there anything, bearing in mind the confusion between ports on a network switch and ports when it comes to internal routing of data, is there something else we should call the ports on a network switch?
There really isn't, because the trouble...
Something else as well, isn't it?
The trouble is, when you're configuring managed switches, every part of the GUI in the interface refers to them as ports.
That's really, yeah, okay. So you just have to be clear of the differential. In
general, we don't tend to configure port numbers. I'm trying to think. software that we all use on our shows, the only one I can think has two things I can think of readily definable ports. Radio World, you can change the port number. And QLab, when you set up a network device, you have to say which port number you're sending the message to.
But we do use it when it comes to filtering, don't we?
Is that the same as Digico, Russ, when you set the send and receive ports on the network when you're controlling it?
No, but kind of. It's another use of a destination location within the device.
I guess it's a thing for the next session. But I mean, I know that like when we've been trying to filter stuff going to the S6L to keep erroneous data out of the ECX bus, we've done port filtering and stuff, haven't we?
Yeah.
Yeah. Okay. Well, just as long as everyone's clearly aware that port can refer to two completely different things, I guess.
Yeah. Sort of why I labelled it.